Alright class, so last time we started the hypothesis testing notes, and we got through the steps of going through a hypothesis test. Keep in mind again that really the math inside the set of notes is not new, we're just formalizing it. One of the things that we have to talk about before we can do a couple more of examples of hypothesis tests is the two types of errors. Or in a sense, when you have data collected and you make a decision based upon it, we could actually be making the wrong decision. So we're going to start by looking at something that's probably a bit more familiar with you, and that's the idea of someone being tried for a given crime. So generally here in the United States, someone is innocent until proven guilty. And so the null hypothesis, or what we're going to assume to be true, is that they're innocent. Why we're actually having the trial is to show that that person is guilty. So that's kind of why that would be our alternative hypothesis. Now in this situation, there are two possible errors that we could commit. So we could find the person guilty when in fact they really were innocent. So what would be so bad about that? Well, of course, we're punishing an innocent person, so that's definitely not a good thing. And if we punish an innocent person, what kind of punishment might they get? Well, they might lose time. So if they go to jail, they're going to lose time. Maybe they lose money on some type of fine. Or maybe it's just something small, but they still end up having their reputation hurt a little bit. And all of these things are bad because the person didn't really deserve it. Now our other verdict that we could have is to find someone not guilty when in fact they really are guilty. Notice we never actually say that someone's innocent, we just say that they're not guilty. So if we have this happen, we're letting a guilty person go free. Which of course is not good. What bad things could happen here? Well, maybe there's the repeat offender. Maybe someone else pays for the crime. Oh, well, so I mean that might be things that could happen. So which of these two errors do you think is more serious, the first one or the second one? My answer students don't generally like, because I'm going to tell you my mind, but it depends. It depends on two different things in my mind. The first thing that's going to probably make a difference to me is the crime. If we're talking about someone who committed murder versus someone who maybe stole money from petty cash, that's going to make maybe a big difference to me on which one I think might be worse than one. The other thing is what perspective that we're coming at it from. So for example, if you were the defendant, which one would you be more upset with? Okay, you're going to be much more upset if they find you guilty when you're actually not guilty. Right, so that's going to be the first one's going to be much more upset for you there. Versus maybe if someone hurt someone in your family, maybe now the second one is more serious in your mind. So I'm going to sort of argue the perspective that we're coming at it from as well as the crime itself. Or how that's going to relate when we just look at statistics, is the situation's going to make a difference to me and which perspective I'm coming at it from. For example, the business owner versus the customer. That might make a difference on which angle I'm coming at something from, on what might be worse in my mind. Now these two types of errors in the statistics world are not creatively named. They're called type 1 error and type 2 error. So generally I assume that you know what an error is. What you just need to remember then is which decision goes with which. So a type 1 error happens if you reject the null, or how we've also been writing if we believe the alternative. Why that's an error, the null is actually true. Versus a type 2 error happens when we don't reject, or in a sense we don't believe the alternative. When the null is really false. So that's the error part of it. So my little way of remembering it, of which is which, so the type 2 error happens when you fail to reject the null hypothesis. So maybe a little way of remembering that. Because usually as long as you can remember which decision goes with which, you'll remember what the error actually is. Now the chance of a type 1 error, or the probability of a type 1 error, hopefully you guess we want these numbers to be small, right? We don't want to make a wrong decision very often. So the chance of a type 1 error is our alpha, that significance level that we've been setting. So a lot of times we've been using 5%, for example, for that alpha level. The probability of a type 2 error is beta. So that's a new symbol. You haven't seen that one before. The one thing to note is it's not 1 minus alpha. And the last term I like to talk about while we're talking about errors is what's called power. What I want you to know about power is it's actually a good thing. It's when you reject the null, or again believe the alternative, when the null really is false. So you're making a good decision here. Or in a sense, you're finding someone guilty when they really are guilty. So it's a good decision there. Alright, so how do these things summarize? So we're going to draw a little chart here to summarize what's going on. So what we have first is there's the truth. Either the null really is true or the null really is false. Right? Or in a sense, our defendant actually either is guilty or is not guilty. So I mean, they have to fall into one of those areas. And then, of course, we have our decision. So we can either reject the null hypothesis or fail to reject it. So we're going to get our little boxes here. Alright, so let's go through each of these. So if I reject the null hypothesis, when the null hypothesis is actually true, is that a good decision or a bad decision? So that's finding someone guilty when they're actually innocent, so that's a bad decision. More specifically, this is going to be our type 1 error. Now, if we reject the null when the null is actually false, so that's finding someone guilty when they really are guilty. So this is no error is happening here. More specifically, that's that power that I just mentioned. If we don't reject the null when the null is really true, or in a sense this is finding someone not guilty when they're innocent, good decision, right? So there's no error if we fall in that box. Finally, if we don't reject the null when the null really is false, or find someone not guilty when they really are guilty, this is our other error here. So those are the 4 things that could happen. Now, in reality, you're either going to be in one column or the other. So think about it from this perspective. When you're trying someone for a crime, either they're innocent or they're guilty. They can't be in both columns at the same time, right? Either they really are innocent or they really are guilty. So generally only one of these columns is actually going to be true. The fun part of a hypothesis test is we don't know which one is true. So if we knew which box we were going to be in already, there'd be no sense in conducting the test. So we don't know which column we're in, but we only can be in one of those columns. All we can do is collect our data to make our decision over here, and hopefully most of the time we're going to end up in our 2 good boxes and not very often end up in our bad boxes. So what are the probabilities of these things happening? So we said probability of a type 1 error was alpha. The probability of a type 2 error is beta. The probability of power is 1 minus beta. And the probability of this no error is 1 minus alpha. So what you'll notice is that each column adds up to 1 because we can only be in one column or the other. So that's why that's happening here. So if we don't want alpha and beta to be very big numbers, what can we do? Well, one thing to note is that we do control alpha. I can set my significance level for the problem. So if I find out a type 1 error is very bad, I can set my alpha to be a very small number. So why don't we just always make alpha small? Well, the problem is generally if you make alpha smaller, you're going to be making beta bigger. So or in a sense, if I make the chance of this error small, the chance of this error is going to get bigger. So that's why we don't always make the one small. The one way to make them both smaller is to increase your sample size. So the more data that we collect, the better chance that we're going to make the right decision overall. So how do I know what alpha to actually set? So if you're going through what a type 1 and a type 2 error would mean, if you find out that a type 1 error is worse, then generally we set our significance level to be a smaller number, such as 1%, or 0.01. If you find out that a type 2 error seems to be worse, what do? So if a type 2 error is worse, that means I want beta to be small. Well, beta is not something I control, so what can I do? Well, if I want to make beta smaller, so I want to make this a decrease, I'm going to have to increase my alpha. So a larger alpha will give me a smaller beta. So generally 10% is about the highest we see for a significance level. There might be times that you go through though and the errors seem to be equal. One does not seem to be worse than the other. And that's when you see issues at standard of 5% or 0.05. So now that we've talked a little bit more about these errors, let's see how the errors apply to a problem that we've done. So in the last video, we were doing example 1 that was looking at the percent of people who approved of Hillary's running for president. So I'm going to go ahead and write out what those hypotheses that we had were. So there we had the null hypothesis was that it was 28%, which is what it was in 2008. So in a sense saying her approval percentage stayed the same. The alternative, we wanted to see if more than 28%, so if her support had increased this year. So let's talk about what each of those errors would mean here in the context of that problem. So first, let's just talk about what a type 1 error would mean. So a type 1 error is when we reject the null when the null is actually true. So what that would mean here, so if we reject the null, we're going to believe there is more support. So rejecting the null, we believe that there is more support for Hillary now. What makes it an error? There really isn't. So if we think there's more support for her, and there really isn't, what bad things could happen because of that? So she might end up wasting money just to end up losing, right? So that would be a bad consequence. Maybe because people think that they're supporting Hillary, maybe other candidates, at least on the Democratic side, decide not to run. And maybe she wasn't our best candidate. So there's some bad things that could happen if that error were committed. Now for a type 2 error, So type 2 error is when we don't reject, but the null really is false. So that would mean we believe there is not more support. For Hillary in 2016. What makes it an error when there really is? So what bad things could happen if we don't think there's more support for her and there actually is? Well, maybe for one, she decides not to run, and maybe she would have won. So that would be a downfall. Or either she decides to run, maybe if people don't think that she's being supported, they're not going to donate money for her. They don't want to support someone they already think is going to lose. Alright, so looking at those two, does one of those seem much worse to you than the other? And keep in mind, the perspective might make a difference. If you're Hillary Clinton herself, or if you're maybe one of the Republican candidates, maybe one of those is going to be different when it comes to which one is worse. From my perspective, as just someone who might be voting, they don't really seem to be much worse in my mind, which is why a lot of times we use that 5% for our significance level. Alright, so that really is the new part in this video. The last thing we're going to do is a couple more of examples, because a lot of times just doing it multiple times helps things make a little bit more sense. So again, if you're not a story problem person, sometimes just highlighting things as we go can be helpful. So example 3. In 2012, it was reported that 69.1% of U.S. adults are considered overweight or obese. We wanted to determine if the proportion of adults in Kentucky that are considered overweight or obese is significantly less than this. We take a random sample of 525 Kentuckians and find that 351 are overweight or obese. So I've kind of highlighted some key things. Let's write down what these are. So this is telling me what it is for the entire United States. That's going to be our P, our 0.691. We want to see if it's less than this. So that's our goal. We take a sample of 525. And then from here we can find our P hat. That we're going to use later. So again, sometimes just writing down what the numbers are can help. Alright, first question is some older stuff here. Who do you think is the population of interest? Who is the entire group that we are trying to study? Well, we want to determine if the proportion of adults in Kentucky that are considered overweight or obese is significantly less than that. So who's the big group that we're looking at? Our adults in Kentucky. That's what we're looking at. Would you consider our sample to be representative if my 525 people came from cardiac unit patients at Kentucky hospitals? So this goes back to that fundamental rule for using data for inference. So what I want to know, or what I need to think about here, are our patients of cardiac units different when it comes to their weight? Do you already have any expectation of how their weight would compare? Yes, they are different. Right? They tend to be heavier. Generally, cardiac patients have a tendency to weigh more than your typical person. So do I consider this sample to be representative? It's not a relatively random and unbiased sample due to what we just explained up here. But now, assuming that I did not do that, let's going to test the appropriate hypothesis using a 5% significance level. So I'm giving you here your alpha to use of 0.05. Right, so our first step for our hypothesis test is the hypotheses. So our null hypothesis and our alternative hypothesis. The alternative hypothesis, if you remember, is the goal that we're reading the problem. So we want to show it's significantly less than this. So we actually wrote out our goal already. This is our alternative hypothesis up here. Now the null hypothesis has the same symbol, the same number, and always an equal sign between them. Or in a sense, the null hypothesis is that Kentucky is the same as the rest of the United States. The alternative is that they are less. All right, our step 2 is that decision rule, which stays the same. So it's reject the null and believe the alternative. If our p-value is less than alpha, our alpha we labeled as our 5% over here. Now again, this is always a less than. It does not matter what the alternative hypothesis sign is. This one is always a less than. You can tattoo it on your arm. It's always less than. All right, step 3 starts with our conditions. Now, as a reminder, conditions are always on your formula sheet. So let me pull up the formula sheet real quick. So here's our formula sheet. I'm going to scroll down here just a little bit. So we're in this proportion 1 sample because we're still working with categorical data. Proportions always for categorical data. We're doing a hypothesis test, so this is going to be the row that I'm going to be in. So here are my conditions. Here's going to be my test statistic. That's also part of step 3. So here again is just the list of my conditions. So we already have our relatively random and unbiased sample. So they're doing a simple random sample. And then we were just told to assume that it was representative. So we're assuming it's not biased from what's stated in the problem there. Then we need to take our n times our p0. So our n is our 525. Our p0 is the number that shows up in the null hypothesis. So that's our 0.691. So we get about 363, which is at least 10. Our n times 1 minus p0 gives us 162.2, which is also at least 10. Next part of step 3 is our test statistic. So kind of quickly label, so this was our conditions. Now we're going to do the test statistic. So first, the formula we see on our formula sheet. So I'll just go ahead and write it out here real quick. Looks like that. We already have our p hat that we found up here. Our 0.6686. We just said our p0 is the 0.691, and our n is the 525. And now we've got to do the math attached to that. So I'll do the numerator and denominator separately here for you so that you can check in case you're not getting the same thing as me. Should get a z-score of about negative 1.11. Then in step 4 is for us to find our p-value. So this is where I draw the picture. Our conditions are met, so I can do it. We're drawing our picture now based upon z. Z is always centered at 0 because, again, the mean is 0 standard deviations from the mean. We take the number we just found and I put it on my plot where it belongs. And then we ask ourselves if we're doing a one-tailed or a two-tailed test. And that's, again, where the alternative hypothesis is important. So we're only looking in one direction, not the two-tailed. And then it points the way that we're going to shade. So we're going to shade to the left. So that shaded area represents the p-value that we're going to find. We're, of course, going to get that number from looking at our table. Our picture shaded left and our table shaded left. So I got to go straight to my table and look up negative 1.11. So here's the negative 1.11 here. So I get 0.1335. And at that point we're done with all the math. We're just going back to step 2 now. So looking at my p-value, is it less than 0.05? No, it is not. So we are going to do what we call fail to reject the null. Or in a sense, we're not going to believe the alternative. Alright, so our last step is the interpretations. There were 2 interpretations here. The first one starts with that at the alpha. So our alpha level changes. That's going to change what our decision may be. Then we're either going to say it is statistically significant or it's not. And that's based upon our decision up here. So if we reject, it's statistically significant. If we fail to reject, it is not statistically significant. To support. And the last part is our alternative hypothesis, but in words. So there is not evidence to support that less than 69.1% of Kentucky adults, because that was our population, are considered overweight or obese. So again, the pieces to that: alpha, whether or not it's significant, alternative hypothesis. Our other interpretation is the one that we were a little bit more used to. And it's one that starts with assuming that the null hypothesis is true, or assuming that Kentucky is the same as the rest of the United States. The probability. And again, just a reminder, we're basically interpreting this picture. So the probability that our data, so our data was used to calculate that negative 1.11, was at least 1.11 standard deviations below that. I'm saying below because it was negative. So again, we interpret what the negative means, not actually leave the sign there. So the probability of that happening was about 13.35%. So if you look at our first three examples that we finished, I've actually done an example of every type of hypothesis test that you could see. And by type, I mean looking at your alternative hypothesis. Example 1 had a greater than sign as the alternative hypothesis. Example 2 had the not equal to sign, or our two-tailed test, which was a little bit different. And then here example 3 has the less than sign. So you've seen an example of every alternative hypothesis with the first three examples. But we're going to go ahead and do one more example. So Diet Dr. Pepper claims to taste like regular Dr. Pepper. So if we're going to assess this, we took a random sample of 245 soda drinkers in northern Kentucky. They did a blind taste test of both sodas, and they had to tell us which one they believed was the Diet Dr. Pepper. So our first question here is, who do we think can be our population of inference? Or in a sense, which larger group here can we represent? So let's start by looking at our sample and figure out what we can and cannot feel like we can do. So first, do you think being a soda drinker is important in distinguishing it? So are soda drinkers and non-soda drinkers going to be just as likely to identify which one? So is this part important? So we need that part. What do you think about the northern Kentucky part? So how big can we get on northern Kentucky? Do you think northern Kentucky is much different than the rest of Kentucky on their ability to identify regular versus Diet Dr. Pepper? Okay, probably not all that different. Kentucky different than the United States? So maybe we're okay with U.S. at this point. Is U.S. the same as the world on their ability to identify it? Okay, probably not. They make sodas a little bit different in other countries. So maybe my overall population here, I'm going to say, is U.S. soda drinkers. So even though we're only taking our sample from a very small region, we can probably actually use this to generalize to a much larger region. Right, from reading this example, could you already figure out what the hypothesis should be? This one's generally a little bit harder for students because you don't really read like a greater than or a less than or a not equal to in there anywhere. You're not actually given that number for the hypotheses. So what are we going to look at here? Well, let's actually first talk about what they're going to be in words and see if that helps us figure out what they're going to be symbol number-wise. So our null hypothesis is their claim. They can't tell the difference. And then the alternative hypothesis would be that they can tell the difference. All right, and so I'm going to let P represent my population proportion that correctly identify the Diet Dr. Pepper. Or in a sense, they correctly identify both of the sodas here. So if I think about it from that way, let's figure out if we can think of what our null and alternative hypothesis would be symbol-wise. So if people can't tell the difference, how often are they going to get it right of which one's the Diet Dr. Pepper? Well, there's 2 cups, so if I just take a guess at which one's the Diet Dr. Pepper, even if I really have no idea, I'm going to get it right half of the time. Right, so that's what's going to happen just by guessing. So I can't really tell the difference if I'm just guessing. Now, when is it going to mean that I can tell the difference? So I need to figure out, do I want a less than, a greater than, or a not equal to here for that alternative hypothesis? Because we're going to have the same symbol and that same number. We just got to figure out which sign goes between them. So let's think kind of both ends and see if both of them make sense. If they get it right less than half of the time, what would that actually mean? That would mean they horribly can't tell the difference. That would mean they would actually think that the Diet Dr. Pepper is more like the regular Dr. Pepper and the regular is more like the Diet. So they're doing a horrible job of guessing correctly. Now, if we really can tell the difference, we should get it right more often. So our alternative hypothesis is going to have that greater than sign. So here we're better than guessing. Alright, so now that you actually know what the hypotheses are, so kind of going down here into step C, see if you can go through the 5 steps and see if they make sense, if there's certain places that you're getting stuck. So pause the video here, I'm going to work it, then we'll come back and see if we agree. Alright, so let's see how we did. Step 1 we already had above there in part B. Our second step is that decision rule. Our significance level this time was 1%. Again, always a less than sign there. Conditions. So we have our simple random sample. There's no known bias from what we're given. Our n times p0. So again, n's 245. P0 number that shows up here in the null hypothesis. Both those numbers check out to be at least 10. Our test statistic starts with our p hat, which was the 148 out of the 245. So we get 3.28 for our test statistic. Step 4, drawing our picture, centered at 0. Number we just put on there. Alternative is only looking in one direction, more specifically to the right. So we have to do the 1 minus rule when we go to the table to get a p-value of 0.0005, which is less than our 0.01. So we will reject the null and believe the alternative. Now looking at our step 5, so our first interpretation, so at our alpha equals 0.01 level, there is, and we're saying is, because we rejected the null up here, statistically significant evidence to support that our U.S. soda drinkers can taste the difference between regular and Diet Dr. Pepper. Second interpretation, we're interpreting this picture. So assuming people cannot tell the difference between the regular and Diet Dr. Pepper, the probability that our data was at least the 3.2 standard deviations above that, again above because it's positive, is 0.0005. Right, now in case you're worried that the math might trip you up, I was actually going to show you that there's a way to check what we're doing here in StatCrunch as well. So you have these directions at the end of your notes, and so we'll do it for this example as well as example 3. So we're going to bring up our StatCrunch, and then we're going to go to Stat, Proportions, 1 Sample with Summary. So I bring up my StatCrunch. I'm just going to open it up here real quick. So we go to our Stat, Proportions, 1 Sample with Summary. Then we're going to enter in the count of successes and the number of observations. So what those two numbers are that we're going to enter are the two numbers that create p hat, so the 148 out of the 245. Right, next it says to click the number, enter the number in the null hypothesis and the sign of the alternative. So what number do we have in the null hypothesis? We have 0.50. What sign do we have for the alternative? We have that greater than. If you put in the wrong sign, you're going to get a different p-value. So that sign's going to drive what your p-value looks like. Those are the only numbers I need to enter in here. And then I can hit compute. And those are the numbers that we see here. So these are going to be within rounding. They might be a little bit different. So first you're going to see the numbers we entered. It's going to spit out the hypotheses, so you can make sure that matches what you have there in step 1. We get a sample proportion of 0.6041 that we used in the problem. You get a standard error of 0.0319. What is this number? Well, this is the number that's on that bottom, that square root part that we had in our test statistics. That way, if you're getting that number wrong, you can double check that you have that one correct in your formula here. Then we're given our z-stat, so they got 3.26. We got 3.28, so that's pretty close within rounding. We got a p-value of 0.0005. They got a p-value of 0.0006. So again, really close that we have there. Let's do the same thing for example 3. So with our new data here, let's look at what we got. So I'm going to go to the same place, my stat, proportions, 1 sample with summary. I'm going to enter my values that you use to create p-hat. So the 351 out of the 525. Then we need our number in the null hypothesis, 0.691, and our alternative sign, which was a less than. And notice how to automatically change that number. Like I said, it's always the same number in both. We had the less than sign. So I hit my compute. So there's our p-hat of about the 0.6686 that we used. Again, that standard error is that part of the denominator of our test is that 0.0202. So really close to what they have there. Their z-statistic we got was negative 1.11. That's also what we got. We got a p-value of 0.1335. They got a p-value of 0.133. So again, really close. Nice ways of double checking your math there. Hypothesis testing generally does take practice, especially the interpretations. But what I will say, I find that students have a tendency to struggle at that same step every single time. Which step that is depends upon the student. So a lot of people get stuck on just getting step 1 and kind of once they have step 1, they're fine. Some people get more troubled with the math. Some people are more troubled with the interpretations. So the only way you're going to find out if you're getting this is to make sure you're working some problems on your own as well.